Welcome to a lesson with Dr. Powell. We're going to look at a rule called LHopitals rule, and it's used for computing limits of fractions where the top is going to 0 and the bottom is also heading towards 0. There's another case of LHopitals rule that also works when the top and the bottom both go to infinity. But right now we'll give some motivation in this little video for what we're going to do and why it works. Okay, so let's suppose, for instance, that we have a function, and I'm going to let the input variable be t, and then a bottom function, input variable t, and we're trying to take this limit as t approaches 0. And as t approaches 0, we'd like this guy to go to 0 and this guy to go to 0. Let's kind of make a picture of this in the xy plane. Suppose that we kind of think about pairing our pairing like this: g of t comma f of t are 2 points as a coordinate pair. Well, this is like the x value and this is like the y value. And then for different values of t, let's assume that f of t and g of t are smooth functions of t, or continuous, smooth meaning differentiable. And so that as t changes, this changes a little bit, that changes a little bit. And the effect is, as it moves around, is you get a kind of a curve. And as t approaches 0, like maybe t is at some value here, but as t approaches 0, this curve is going to head toward the origin. See why? It's because this coordinate is going to 0 and that coordinate is going to 0. Okay, so let's just think a little bit about this for a minute. Now, this fraction right here then is kind of like a y value over an x value, or kind of like, if you map this out, isn't it like the f of t is kind of like a change of y, and g of t is like a change of x, right? Because g of t is this x value, f of t is that y value. So really, when we take this fraction, we're looking at change of y over change of x as we go from here to the origin. Now, what happens as we move along this line? Maybe right here, maybe right here. As we move along the line, and we look at this slope as we get closer and closer, the slope actually, so imagine you have a curve here, and suppose this is the origin. So the slope from here to here over time matches what the tangent line is to the curve. So that's kind of where we're headed. So this limit right here of kind of like the rise of a run in this particular situation actually heads toward, or is actually equal to, the slope of the tangent line to this curve that we've just developed with taking this as our x value and that is our y value. So if we were able to compute the slope of this curve at that point, that's another way of actually expressing what that limit is. So how do we do that? How do we get that slope, the slope of the tangent line right there? Well, what we can do is we can take let's just think about a little bit. We want to change, basically what we want is how much is f changing over how much is g changing? Because how much f's changing, that's how much y is changing, and how much g is changing, that's how much x is changing, right? Kind of like our dx and our df. So we kind of want a ratio of these two guys. So think about df as being like the rise of the output on the tangent line of f with respect to t, and similarly for g. So what if we fix one specific run of t and call it dt? Then the ratio, so let's suppose that dt is a fixed value. So for this one dt value, you get that much rise of dg. For this one, you get that much rise of df on the respective tangent lines. Then if you're looking at a relationship, a ratio of, well, if g changes by this much, how much does f change? It's actually just this ratio, because dt is affecting the same. If we let dt be the exact same, then the effect that dt has on dg, is, that's how much g changes. And for that same change of g, which is affected by that dt, which is the same dt here, you get that much. Basically, we can think about canceling here with thinking of those as the same dt's, and thinking at least on tangent lines for ratios with none of these guys being 0, you'd get this ratio right here, df over dg, which is exactly what we want, dy over dx, which is the slope there. So this right here, we can interpret this as being f prime of t, and you can interpret this down here as being g prime of t. So what do we get? We get that the derivative of, or the slope of this line is actually the derivative of f divided by the derivative of g. Notice that we don't take the derivative of the whole thing. We take the derivative of f divided by the derivative of g, and we look at that. And this in and of itself, if we can compute it, should be this limit. Now, if we can't, then, but this ratio will still be the right one, and we just need to take a limit of it. And if that limit exists, that limit will be equal to this limit. So we get L'Hopital's rule is actually the following idea, that if we take the limit of a fraction, we can change this to the limit of the fraction of derivatives. So we're going to use this rule. Now, again, remember this rule right here, as we've motivated it works for if the top is going to 0 and the bottom is going to 0. So next we'll look at some examples. Thanks for watching.